Hello, my name is Tim Matson. I'm going to talk about why we need OpenMP more than ever. And I'm going to do this by quickly brushing through the history of parallel computing to try and ground where we need to go tomorrow based on where we've been yesterday. So let's go. I'm going to try and move fast. So here we go. The modern era of parallelism began when we started building parallel system from commercial off-the-shelf microprocessor, COT microprocessors. That changed the world. And it all started at Caltech back in 1981 when Jeffrey Fox and Charles Seitz developed the Caltech Cosmic Cube out of, Intel 8086 and 8087 processors. And it was a game changer. And it completely changed the cost function of hardware. And it led to, in the late 80s, the mid 80s actually, to cluster computing, which meant all of a sudden HPC systems were everywhere. Now, this led Eugene Brooks at SC90 to coin the idea of the attack of the killer micros. And I love this phrase, and it kind of sets the stage for what it looked like from the context of a mainframe manufacturer like Cray, what it looked like when all of a sudden these off-the-shelf, cheap, inexpensive microprocessors were doing HPC. Now, this led to a situation where everyone, it seemed, wanted to create their own parallel programming environment. And there was this glut. And here I show this funny list of, I just went through and looked at all the environments I saw in conference proceedings throughout the 90s. And it got ridiculous. It really did. And this created two problems. For application developers, it meant they had to waste time figuring out which programming model to use. And that consumed a lot of time. And then if they made the wrong choice when they moved to a new system, they'd have to port their software. But another thing this did is vendors obey their key customers, the people who are going to give them a lot of money. If they say, I need this particular programming environment, then the vendor has to support it. And what it means is vendors are chasing programming models instead of making the ones we all have and depend on actually work better. So it actually decreased the stability and the quality of what application developers had to work with. Well, then a brief moment of sanity prevailed. And the details are on this slide. I'll gloss over it quickly. But you had this grand convergence of the vendor community and, really important here, the user community, the application community. They came together and said, no, we need to come up with a single standard that will handle everything we need to do with these cluster-based systems. And of course, that led to MPI. And it came out in 1994. And because Bill Gropp and Rusty Lusk, during the meetings of the MPI forum, had built a reference implementation called MPI-CH, once the standard came out, we immediately had systems supporting MPI out and running. And I can't stress enough, it was that collaboration between the application developer, the user community, and the vendors that made it happen. Then, not too many years after that, we faced the same problem that we had in the cluster world. We faced it in the shared memory programming world. And each vendor had their own shared memory directive set, and it was a nightmare. So vendors came together and with the user community, except this time the user community came from the Accelerated Strategic Computing Initiative, or ASCII. And what that meant is they had some muscle because a lot of funding passed through the ASCII program. So when the developer community in ASCII said, come on, guys, let's agree on a directive set, they had some strength behind that, and it happened. And so by 1997, OpenMP came out, and it was supported widely across the market shortly thereafter. So this partnership between vendors and the applications community joining together works. And 25 plus years later, you look at it, and this is a study, the reference is the bottom of the slide. It looked at GitHub repositories between 2013 and 2023. And look, OpenMP, 25 plus years after it started, is 45% of all parallel programs in GitHub, and MPI is 27.1%. So this strategy really, really worked. Before I leave this slide, I just want to point out, I think we undercounted CUDA, so I want to be really, really honest about that. So I think CUDA might be a little bit higher, but not much, because we're only looking in this figure at direct programming. And of course, the power of CUDA is most people use it without knowing they're using it because it's hidden behind an API like PyTorch. But at any rate, this strategy of vendors and developers coming together, creating a programming model, oh my gosh, it works. So when GPUs showed up in 2006, we thought the same thing would work. Vendor community getting together with the user community. In this case, it was really focused around Apple, so it was the consumer laptop products mostly. But several of us on the vendor side were pushing from the application developer community on HPC, and we thought it would really work again. I remember my friends at NVIDIA telling me that the belief was that there was no way CUDA would ever take off in the broader community because people wouldn't use a proprietary API. Boy, were we wrong. OpenCL worked in gaming and embedded space, but it didn't work in HPC. If you look today, if you go to work with a GPU, it's so frustrating because you have people pushing CUDA, OpenACC, OpenMP, SYCL, OpenCL, and more. So it's this messy situation of developers are like, well, what should I use? So it's really, really tough. And the other problem is that I want you to internalize is these days, AI controls everything, not HPC. So you're not going to get the vendors investing a lot and putting a lot of effort into giving HPC people a really good solution for the GPU programming. So this is what happens when the applications community doesn't really push and speak with one voice and line up behind a small number of programming models. You get the failure that was the OpenCL in HPC. So I want to emphasize, based on this little walk through history, how incredibly important it is that we have less is more. The fewer programming models, the better. I need you application developers to avoid the new hot, sexy thing. You stick with the small number of models. And I want to emphasize, you have far more power than you think you do, but not if you let the world divide you. You really need to come together, like in the old days with the ASCII community, speak with one voice and make things happen around a small number of programming models. Okay, I want to quickly move on that we live in a world constrained by power, and that means heterogeneous computing. Okay, let me develop this idea for you a bit. This slide and the reference at the bottom takes a single precision matrix multiply, and it runs it on a highly specialized matrix multiply specialized silicon from Movidius, a GPU, and an Intel Xeon. And these are all from about the same era, the same process technology. And you see something that's pretty obvious, but I really like data to drive things home, and that is silicon doing what it is designed to do, what it's specialized to do, is more power efficient than general purpose silicon. So this isn't saying that Movidius is better than NVIDIA is better than the Intel Xeon. No. But it is saying that gigaflops per watt does better on the more specialized parts when they're doing the work they're specialized to. This is what leads to the importance of heterogeneous computing. So imagine I have this collection of tasks with the colored bars running on a CPU. The GPU world will tell you all the time, just offload, get it off that stupid CPU and run on the GPU. Or how about this, heterogeneous computing, where you look at each of those tasks and you say, which processor is best for that task? And then you mix it all up. So you run some of it on the CPU, some on the GPU. That's heterogeneous computing. And today, OpenMP is one of the only models that cleanly supports CPU and GPU programming explicitly within the same model. So OpenMP is great for heterogeneous computing. And if you look at the vendor community, they are completely on board. Now, you'll have access to the slides. Obviously I could spend 5 minutes just talking through this slide. I just want to point out that NVIDIA's been pushing this for a while with their truly excellent Grace Hopper super chip, where you have an array of ARM cores and an array of GH100 GPU chiplets, all integrated into one package with a uniform memory architecture. Marvelous chip. And they're pushing this architecture forward. They're very dedicated. If you look at their product line, they're really dedicated to pushing this further. But AMD has the Instinct products, and their slogan is that this is the world's first integrated data center CPU and GPU. Now, what they mean there is they don't have an ARM core for the CPU. They have a full-on Zen CPU. So that's their Zen 4 CPU, which is their server class CPU with their high-end GPUs. And they have coming out in 2026 a major upgrade in the MI400. And in 2028, we'll have the Discovery supercomputer at ORNL. And notice it's going to contain these unified memory architecture CPU GPU chips as well. And now Intel's getting in the game with NVIDIA. This one is fascinating to me, a chiplet architecture where the chiplets come from 2 different vendors. This is awesome. And they just announced this in September 18th, 2025. So this is very, very new. There'll be a client part where we have an Intel x86 clients part with the GPU from NVIDIA and RTX. But they've also teased us by talking about how there'll be custom x86 Xeon CPUs. That's Intel's server class CPU, tightly integrated and specialized to work with NVIDIA GPUs, probably connected through NVLink. So we don't have a lot of details yet, but what this shows you is all 3 of our major processor vendors are already on board with heterogeneous computing. It's the future, guys. So that means we really need programming models that can dance back and forth between CPU and GPU. And the only option I know of today is OpenMP. It works. I've done it. I've used it. It works. I take a program and one loop goes to the CPU, one loop goes to the GPU, and I just seamlessly integrate CPU and GPU. So I want to emphasize heterogeneous computing in a power-constrained world, which is what we live in. It's critical that we can not just do offload to an attached accelerator. No, that we mix up the workloads so the best piece of the work runs on the best processor for it. And OpenMP is one of the only ways to do that. So I want to quickly move on to my last point. And that is there's this attitude I see that C++ is going to take over and HPC, that's the future. And it's like, come on. There never has been and never will be one programming language to rule them all. It doesn't work that way. And so here I show the PyPL data. It's about 6 months old, but it tells you what many of us who spend time looking closely at the application world know, which is Python rules, dramatically rules. That's a logarithmic scale we're plotting those different lines. Python dominates, and C and C++ are way, way down on the list. So we really, really need a programming model that's independent of the language. So as you move from one language to another, you can take the same algorithms, the same parallel programming mindset, and carry it across languages. OpenMP is pretty much one of the only ones that does that in an open, portable standard. At least we cover C, C++, Fortran, and recently, and I have the link at the bottom of the page here, recently we also support Python. And there's an OpenMP language committee looking to make that support official. So I just want to summarize quickly, less is more. Application developers, you hurt yourself when you use a diversity of programming models. MPI, OpenMP, maybe stop. The fewer, the better. You'll make your life better if you do that. We got to think heterogeneous computing, where we break up our workloads, our programs running on a CPU and a GPU. And look, no single language will ever rule. So I know they're doing wonderful things in C++ with parallel programming, but not everyone uses C++. And what do you tell them? So we really need a programming model that can move between languages, and OpenMP does pretty well on that today. So just closing, I write books, so got to close with my book advertisement. But really, if you're just getting started, you start with the OpenMP Common Core to get a solid foundation. But then when you want to look at the diversity of constructs covering memory affinities, more details on tasking, the SIMD constructs, and a start at the accelerators, then you go using OpenMP the next step. And then the most recent book in this trio is a deep dive into programming your GPU with OpenMP. So we need OpenMP more than ever, and these books will help you get started. Thank you very much for listening to me.